Hi there. Hope you had a good Easter. You just need to look at that for just a minute before it sinks in. That's a pretty good one. So we're gonna slow down for the next few weeks because really we don't have a whole lot of material left because your EOC test would have been like in 3 weeks. So anyway, this week we're just going to hit one basic topic, and that is population size and how it slows down and increases. And so here we go. So we have an idea that if resources are unlimited, then populations have great reproductive potential, right? And their growth can do this mathematically exponential thing. This exponential model, right, is we introduced this in evolution because great reproductive potential is part of one of the table setters for the natural selection process, right? Um, so here we have, notice, this word population in this unit is now being used more in terms of number, right? Population size, as opposed to the name that we call a group of same species in the same place and time, a population. Now we're talking about the number of individuals in a population. So here's some very simple math, right? What could cause this population size to change? Well, the thing that would cause it to increase is if little babies get born or if things move in. Immigration is in, right, to that group, whatever we're defining that group as. What would cause the population size of that group to go down? If things die or if things leave, emigrate. That's pretty simple, right? Change in population is the things that cause it to go up minus the things that cause it to go down. And if those are equal, births plus immigration, deaths plus emigration, then we're at that stage we call zero population growth. Not zero population, but zero population growth, meaning it's going to flatline, stay the same. Okay, so in reality, though, right, resources are not unlimited. They're finite. That was another part of the natural selection story, right? So what happens in reality, again in a model, is that this possible exponential growth, the blue line is like what could happen, gets limited by different factors, which guess what? We call limiting factors, right? And it causes a population to reach a size that this environment can sustain or carry. And so this pretty simple term, carrying capacity, symbolized by, for some reason, a K, not a C, right? This is the maximum stable population size a particular environment can support, right? Can your population size go above that? Yeah, but not for long because you're going to run out of something and it'll take you back down to here. Okay? Right. So if we connect natural selection to this graph, right? Here's what starts to happen as you start to increase in population size. Now the shortages of resources starts to determine that some things can reproduce more than others. And so this red line represents the successful individuals, right, compared to all the individuals that could have been, the blue ones, right? The ones that actually are the ones that likely have some kind of traits that allow them to handle things better, whatever. You don't have to worry about all this math here right now. But you see this K, carrying capacity, is an actual number of individuals. So that kind of growth, because of the way that curve goes, like that is you'll do this in math if you haven't already, that is the kind of curve that's called a log curve, logistic curve. So here we have the idea that these things that can limit population size might be living things, biotic, or non-living things, abiotic, right? So this can be a hair tricky sometimes, right? Sometimes very simple, right? What would predators be? Well, predators are living things, so they'd be in the biotic category, right? What is water? Well, water is not living, so it would be in the abiotic category. Space would be in the abiotic category. Temperature and pH, right? These, water and temperature, are big biggies always in terms of limiting factors, all right? What about food? Well, here's where it gets a little tricky, right? Food, right, if we're talking about organic molecules, that would be biotic, because where do those organic molecules come from? Living things. But if we're talking about that part of your food that's like minerals, like salt, right? Well, that would be like abiotic. So just a little tricky, not too much. Don't overthink, right? I'm going to say one more, though, that'll come up later, too. Disease causers. That can definitely limit your population, right? What kind of things can cause disease? Those kind of things we call pathogens, right? Well, pathogens can be bacteria cells. They are living things, therefore they would be biotic. But what else can cause disease? Smoking, right? The chemicals in smoke, all kinds of different chemicals, right, can cause diseases. That would be in an abiotic category. Okay, so do real world populations, do they actually act like this? Well, sometimes, right? Both of these graphs are representations of laboratory experiments and real life things. And this one really perfectly, when you go over time here, the number of these little parameciums, they increase exponentially, but then gradually slow down as they run out of food or space or whatever, right, and reach their carrying capacity. So did these little water fleas, they're called, these little Daphnia. They went up exponentially and they went higher, right? And then they started to run out of food, space, whatever, whatever, and they also leveled off. But does that mean it always happens like this? Not at all, because there's lots of complex factors that can determine your population size. So here we have these little sparrows, and as time has gone by here over 25 years, they have increased exponentially and then at a big decrease. They've increased exponentially. This looks kind of like that punctuated equilibrium thing, except that was about how many species are on the earth, and these mass extinctions, that was a different kind of thing, but a similar pattern. So what might have caused this, right? Well, in this particular case, again, these are all done on real studies, it was periodic droughts, which really reduced the amount of food and therefore caused these drop in the number of individuals. But then once the rain came back and the food started to grow, then they had lots of resources, they could do that. Okay, so some of these limiting factors depend on density, right? And obviously food would be one of them, because the more individuals there are in a particular area, that's what density is about, the less food there is for each individual. So this is an interesting kind of graph here. If you look at this, this is how many females are there around. And these birds have evolved a way to somehow process the information about how many other females are around, so that when there's lots of females around, they lay less eggs. That's what a clutch is the eggs they lay, the clutch size. How many eggs do they lay? Well, if there's a lot of females around, they only lay 3 or so. If there's not as many females around, they lay more. Now, how they have come to evolve that, that's a lot harder to figure out than this fact that density here is having an effect on how many new babies are born in this case. Okay, so here's human population, and you can see look at this break in the graph here. This is 8,000 years BC. So if we go up to like 1000 AD, there's 9,000 years that the population of humans on the earth really didn't increase dramatically, right? But as more humans came on the earth with great reproductive potential, we gradually went into that exponential part of growth, right? And we have been in that really high exponential part for a good while now. Obviously, we're 20 years past 2000, and we're up to 7 billion people on the earth. Where is that going to stop? Well, it's got to stop sooner or later. So one of the things that can determine this, and this is something we're seeing now with the COVID-19 disease, right? looking at not just your population size, but how many people are there of this age compared to this age and this age, right? This is often shown in this kind of a bar graph modification that makes it look like a pyramid if you have a lot less of these than you do of these. So if we look at Kenya here, what this kind of information can allow you to predict, right, is how fast is the population of this particular place likely to grow? Well, if you've got a whole lot of reproducers and not many older people that are likely to die, then you're going to have a lot more births than deaths. So they look like they're set for the exponential part of population growth. If you have roughly kind of balanced number of reproducers and not reproducers, right, then you probably might be on a lot slower path of growth. What would a difference maker be here? Might be healthcare, might be some other stuff too. Now you look at Italy. This is where the COVID deaths really skyrocketed. If you remember, this is just a couple weeks ago, right? Part of the reason was because a high proportion of their population was older and therefore a little more susceptible to the disease. But in terms of just future population growth, if you have few reproducers compared to how many old people you have that can't reproduce, then that means you're going to like flatten out. You might even be decreasing in population.